This is probably one of our more enjoyable experiments that we do in physics. We call it a rocket, but it's not really a rocket. It's really a projectile, and we'll talk a little bit about why that's the case. First, I need to give appropriate credit to our very excellent lab technician, Tracy McCann, who built our rocket for us. There are designs for this guy on the web, and we'll share that with you on the website as well, so that you could build one yourself or get your own very excellent lab tech to build one of those. It's essentially, it's a pressurized device. We're going to put some air pressure in it with our pump, and it's going to fire this projectile some considerable distance. It's got a solenoid that actually allows us to switch and let that air pressure out all in one go. So we're going to pump it to 20 psi each time. So we're keeping the initial velocity of the rocket constant, and we're going to change the angle. So effectively, we've got three different angles, three different front legs to actually compare, and we'll be able to calculate, because you should be able to calculate the theoretical distance that a projectile will go, and from that calculate the initial velocity once you know the angle. So in each case, what I'm going to give you, the length from here to here, the hypotenuse is exactly 70.0 centimeters, and I'll give you the height from the tip of the rocket to the ground, and you can use your trigonometry to calculate the angle there. So that will be relatively easy each time, and then we'll do a couple of trials at each of the different heights. For the purposes of the video, for your own experiment in your own school, you would do probably 5 at each of the heights. We'll do a bit less than that. So this is how it all works. I should mention, we call this one a rocket, but it's not really a rocket. It looks like a rocket. If it were a rocket, it would have an engine that's firing while it's traveling. It would be getting continued increase of velocity as it was traveling. It's not a rocket, it's a projectile. So it gets all its velocity at the beginning and then slowly loses it as it heads toward the ground due to friction and so on. If it were a perfect projectile, in a perfect environment, airless, no friction, then its shape would be a perfect parabola. The slope going up and the slope going down would be the same. Watch for the actual shape of the motion, and you'll see that it's not a perfect parabola, but we can still probably have enough information from the distance that it travels and the initial angle to calculate what the initial velocity is with that 20 psi. So we're going to do 3 different heights, and we'll do a couple of trials at each height, and then from that you can calculate what's the initial velocity produced by 20 psi in this system. The launcher essentially is a system of pipes with just a solenoid that allows us to switch. So we pump it up and then switch and fire, and our projectile is on the end there and just fires out. It's a rocket, it's a rocket shape, it's got these vanes, which again probably help stabilize it in flight, but maybe give it a little bit more drag than if it didn't have them. It should fly relatively straight, but we will see. Let's conduct the experiment. So initially, from the tip of the rocket to the ground point is 830 millimeter, 83 centimeter. So 830 there, and from the tip of the rocket to the ground is 325 millimeter on this particular setting. So note those numbers, you're going to need them. So I'll pump it up to 20. And press the launch button. Okay, that one didn't fly straight and ended up in the bush. Okay, launch the second, slightly straightened, at still that same set of measurements. So 830 and 325 millimeter. I'm pumping to 20 again and hoping that it stays on the lawn this time. almost got our statue, but we didn't. So that one actually, at this particular set of measurements that I gave you earlier, we got 26.67 meters. So that was the distance traveled by the rocket. You probably will have noticed that it went up on this angle, like a golf ball, up on this angle and down at a steeper angle, and in fact stuck into the ground. So it's not a full perfect projectile motion, but it's giving us a sense of the distance that we're actually getting. So we'll try it with a slightly longer leg and measure the angle and the height for the second one. So the distance from the tip down the hypotenuse will stay the same, 830 millimeter. The distance from the tip of the rocket to the ground, this time, is 512 millimeter. So to make a note of those, you're going to need those, and then we will take a shot again at 20 psi. There is a small but finite chance that this one ends up on Smith Street. Let's test it. It's actually a very similar distance. That trial at that higher angle gave us a distance of 25.45 meters. So slightly less than at the lower angle. We'll do one more trial at that angle, and then we'll go to an even steeper angle. So everything kept the same. With remarkable consistency, that one was also 25.45 meters, so exactly the same at the same height. I don't know that that consistency is real at that level of precision, but we'll take it. So that's the second one for that height, and we'll try the really tall one. So a much higher trajectory. Now, the reason I gave you the hypotenuse in the first place is because it doesn't change. This distance along the ground would have kept changing, but the hypotenuse is the same all the time, so 830. Distance from tip to ground, though, will have changed quite a bit. That is a very metal number, 666 millimeters. So we'll take that one. And same deal, we're keeping our initial pressure the same, 20 psi. Okay, tall trial number one. Very high, but it looks just a fraction shorter. That first trial at the higher angle gave us a distance of 22.97 meters. So some 2 or 3 meters shorter than the preceding ones. So that angle clearly is taller than the optimum angle for reaching the optimum distance. We'll give it one more trial at that height and see how it compares. and that one is dramatically shorter. This is obviously illustrating the fact that this is not a perfect projectile in an airless environment. The wind is relevant and the drag is relevant. Well, let's see what it is. That one is 13.18 metres. Make a note of it, but I think we'll do one more trial at that height just to see whether we can get something a little more consistent with either one of those two initial measurements. And I think it's just split the difference perfectly. Let's see. That one is 17.32 metres. So yes, I think if you do the maths, you'll find it's fairly much right between the other two measurements at this height. There seems to be more variability at the highest height. G'day all, just having a look at our projectile motion reactions and equations from our experiment. So essentially we have a situation where we're projecting our projectile at an angle to the x-axis, which is the ground, in relation to the y-axis, which is the sky effectively, a right angle to the ground. It has an initial velocity u, and that's what we're trying to find. So u is just a velocity in meters per second, and that's our actual outcome from this experiment, was to calculate the value of u given the distance that the rocket travelled. We're projecting it at an angle theta to the ground, and using our vector notation we can work out the horizontal component of u, which is the initial velocity in the x direction, which is u, I never remember, so I always have to check my notes, cos theta. And I should be able to get it just from trig, because right angle triangle there, hypotenuse opposite sine theta. So cos is opposite over adjacent. You might remember sine opposite over hypotenuse, opposite over hypotenuse, cos adjacent over hypotenuse, and tan opposite over adjacent. That's how I remember it. So, and then there's a vertical component as well, which is, it's parallel and the same length as this line here, which is the adjacent. So uy is equal to u sine theta. Sorry, I didn't leave myself enough room. You get the idea. So ux and uy, but we don't know the value of u, so we can't calculate those yet. So the things that we're going to have are theta and a distance. Now the path is going to be a parabola of sorts, and we'll talk about that in a moment. But I've probably drawn it as it actually is. It really should be a symmetrical parabola if we were working in an airless environment, but we have air resistance, so it's not. It's that shape, which means that our calculation is going to be a bit flawed, because we're the equations are assuming a frictionless environment, an airless environment, but in fact we have air resistance, and it was quite significant. If you saw the paths of the rocket in the video, it was coming down almost vertically by the end because it had slowed enough. Again, in the airless environment, ux doesn't change. X is constant because there's nothing causing the rocket to accelerate, because it's not a rocket. It doesn't have an engine, so it's given an initial velocity, and assuming you don't have drag, then that initial velocity in that horizontal direction stays constant. In the vertical direction, it's a different story because you've got the acceleration due to gravity. So it starts out with a particular velocity upward, and then the acceleration due to gravity slows it until it stops, and then accelerates it back to Earth. So we need to work out the time that it takes to reach the maximum height, and then use that to work out the time that it takes to return to Earth, because it'll be just twice that time, and also look at the distance. And between the two, we can actually find out the value of u. So let me work through that before we get to the actual data. We've got the data for our measurements. We've got the 3 angles calculated from the measurements that we took, and then we've got the 3 different distances for those different angles. So let's just really quickly, as we said, ux theoretically at least is a constant. And the distance it travels in the x-axis, so the distance before it hits the ground again, is just going to be ux, that constant velocity, times t, the time of flight. So that's essentially what it's going to be. Now, we're going to be able to measure that directly. We're trying to calculate that, and we need to be able to calculate the time, or find that expressed in something that we can measure or know about. So basically, when a projectile, if we just look at the vertical motion, then it starts out with an initial velocity uy, slows to 0. So at the very top point, uy equals 0. Or actually call that vy, because it's a final velocity for that section that we're interested in. So uy equals whatever the value is over here, but vy is equal to 0. And then, as I say, it will take the same amount of time to come down as it takes to go up, because it's being accelerated by the same force, the acceleration due to gravity. So in this case, we can do vy equals uy plus ayt. There's no ax because there's no acceleration due to gravity. In this case, we want 0 to be the final velocity at the top. Uy is just going to be u sine theta at the bottom. And then it's plus minus 9.8 meters per second squared. That's the acceleration due to gravity. That's the value of a, the acceleration in this case, minus 9.8 times t. So now we've actually got, if we rearrange slightly, an expression for the time taken to reach the top of the arc. It ends up being, let's see, take 9.8 to the other side, we get 9.8 t equals u sine theta. Divide both sides by 9.8 to get t by itself. And so we've got an expression for t, but that is the time for half the journey. So in fact, if we go up here, oh no, actually we'll bring our expression 1 down here. S equals ux times t. Actually, let's ux we know is u cos theta, so let's just spread that out. Ux equals u cos theta, and then times 2, because this is the time for a half, so we need to double it, times u sine theta over 9.8. Or we could put the whole thing over 9.8 if we wanted to, for neatness. Now, u times u is u squared. Cos theta times sine theta is, let's times 2. Cos theta times sine theta, this is a trig identity, is equal to a half sine 2 theta. That's a trig identity you would probably need to look up, but it's a good way to solve this thing. Over 9.8. This is s, the distance travelled. The 2 and the half cancel out, so that's convenient. So we have that expression. Now what we want, though, is an expression for u, the initial velocity, in terms of the distance travelled, which we measured, and the angle, which we measured. So how do we get to that? We go 9.8s equals u squared times sine 2 theta. Oh, sorry, I'm doing phi's instead of thetas. Divide both sides by sine 2 theta. Gets rid of that. And take the square root of both sides. And we've got an expression for u in terms of s and theta. Now, the calculations are a wee bit gnarly, so I did them ahead of time. They're not particularly, but what I did was throw this formula into a Excel spreadsheet to get it to calculate the multiple ones rather than do a number of them by hand. So I prepared a table earlier. The angles, let's just quickly work on that. So in the case of the angles, we've got, I'll just redraw our little triangle. Sorry, I'm going to tidy that because it's ugly. But it was all part of the one line. There's our triangle, there's our opposite, there's our hypotenuse, there's our theta. And so sine theta is opposite over hypotenuse, or theta is inverse sine of opposite over hypotenuse. Oops. And the hypotenuse in every case was 830 millimetre, which is what I was yelling out in terms of millimetres, but 0.83 metre in each case. So it ends up being that theta was equal to inverse sine of 325 over 830. You can do 0.325 over 0.830, but it doesn't actually matter because it's a ratio. So you will get the same sign either way. It's worth kind of thinking about that kind of mathematics to make it work. But so that was the first angle with 325, second angle with, I think, 514 from memory, third angle with 666 as the angles. So those are your angles. Those are your values of theta for the three different legs on the rocket. The distances we reached were 26.7. That one was, we only did one trial on the shortest leg. Middle leg, we did two trials and they're identical, 25.45. So I've rounded them to three significant figures and put that. Third one, we got three wildly variant, a 13-ish, a 17-ish, and a 20-something-ish. I've given the average of those. Now, obviously, our results are not accurate because those measurements were quite shonky because of this nonsense, right? If we had no vacuum, we would have a shape like that, and that would be the S that would actually work in the equation. We're getting some subset of it because of friction. So that's what's going on and why we're getting weird results and why our results aren't consistent, because we always pump the rocket to 20 psi. So these answers for you, for the value of the initial velocity, should all be the same. We should be getting the same number for each of them if our experiment was working as the physics expressions explain it. Now, one of the things with projectile motion is just the nature of the beast is that, of course, most of the time we are in atmosphere. We can do it out in space as well, but mostly we're in atmosphere. And the maths gets quite a bit harder quite quickly because you need differential equations effectively to deal with turbulence and air resistance. So for the students at high school level, we stick to these simplified equations that ignore air resistance and work in physics world. But in the real world, we have to take into account the fact that there is that there is drag. We were already taking gravity into account, but not air resistance.
So basically, this one you really kind of are just writing up this. You're not particularly creating a new graph based on this. I don't think that there's any real point graphing theta versus u, because as I say, u is supposed to be a constant, but in fact isn't because of different air resistance, and there was wind and a variety of other factors going on as well. But what you need to do is just understand the theoretical process, particularly this process by which we got from two pieces of information. The information that in the x-axis we have a constant velocity, u equals v, u of x equals v of x, the initial and the final velocity of x should be exactly the same, again ignoring air resistance, and they're equal to u cos theta, and that we've got this expression for the vertical velocity, and we know the fact that the vertical velocity goes to zero at the top. It can't do anything else because it's going in one direction, the upward direction, and then it's going in the downward direction. So there must be a moment when it's stopped in the upward direction and stopped in every direction and just going downward. Now, it's not stopped in every direction, it's stopped only in the vertical direction. So at the very top here, if we draw a tangent line, because that's the tangent line to the velocity, at the very top, where that line's perfectly horizontal, that tangent line is 100% ux. It's 100% motion in the x direction, 0% motion in the y direction. Every other place, it's a mix of this side, it's upward motion in the y direction as well as constant in the x. This side is downward motion in the y direction as well as in the x. But at that top point, it's zero. So not to belabor the point, but I hope that gives you a good sense of projectile motion. We do this experiment with the rocket partly because it's cool, it's fun, it's engaging for the students. We could potentially create a similar thing. I'm not going to say the word, well, I am going to say the word spud gun, but you shouldn't say it around your students. But if you were firing a projectile that was less subject to wind resistance, like a ball, particularly a smooth spherical ball, you might get a more parabolic, a more standard path, less affected by air resistance. Although, a golf ball, it has the dimples, but it's very, very smooth and aerodynamic, and yet you still get this shape, not this shape, when you hit a golf ball. So hopefully that gives you a good sense of the projectile motion problem and the rocket and the non-ideality, but the excellent physics that's there to be learned in this experiment.